So last day we introduced what we call the directional derivative. Which is really the last derivative we're going to introduce in this course. So once we're done with directional derivative, we're kind of done with derivatives, then we're going to switch to integrals pretty quick. And we said a directional derivative is special in that it allows us to calculate the derivative of any function, say z is a function of xy like that. It allows us to calculate the derivative of that in any direction. We said last year that, you know, we said last day when you did derivatives last year, you only found the derivatives in one direction, the positive x-axis direction. That's the only derivatives you found last year. Now we know that we can actually find the derivative in any direction. We could find it if we're talking about a two-dimensional y is equal to a function of x. We can find it in the positive x direction, or we can find the derivative in the negative x direction. If we're dealing in two dimensions, we can find now, or pardon me, in three dimensions, we can now find the derivative in any three-dimensional direction we choose using the directional derivative. Okay? And we said we can find the derivative of this thing in the direction of some unit vector we're going to call u hat. And u hat can point in any direction in three-dimensional space. And the directional derivative will tell us if we move a small amount in the direction of u hat, how much does our function change, and how quickly does it change, actually, right? And we drew a function like this. We said if our function looks something like this, okay, our three-dimensional surface, this is the surface z is equal to a function of xy. And we said if at some point in the xy plane, x naught, y naught, we move in a certain direction, let's do it a little bit different. We move a little bit in this direction, u hat. So we're moving along that dashed line in the xy plane. That dashed line is in the xy plane. And we're moving it a little bit along that line in the direction of u hat. So that means x changes a little bit and y changes a little bit. And we see, okay, how much does z change? As I go from, you know, this point on this line to this point, well, that means z is going to change, say, from here to here. Okay? So basically we said that the directional derivative is going to give us the slope of this tangent line to that surface at that point. Okay? A derivative is just the slope of a line. In this case, it's the slope of a line that is tangent to our surface. Okay? And this line and this line are in the same plane. I don't know if I draw the plane something like that. Okay, they're both in that plane. So as I move along this line here, that is going to trace a curve like this on my surface. Okay, and the directional derivative tells me how quickly does that value z, f of xy, change if I move x and y, change x and y a little bit in this particular direction. I could also find the directional derivative at this point in this direction, or in this direction, or in this direction. Any direction I want as indicated by that vector u hat, okay? So the equation for this line, I can write a parametric equation for this line. I need a vector parallel to the line, well that's u hat, and I need a point on the line, well that's x naught, y naught, right? So I can say x as a function of some parameter, and I'm not going to use t here, it makes more sense to use s, it's just a parameter, is equal to x naught plus s times a, y of s is equal to y naught plus s times b, where u hat is equal to ab. Okay, so A is the x component of my unit vector, B is the y component of my unit vector. So using that vector, using the point x naught, y naught, I can write the parametric equation for this line here in this xy plane. Okay, it's the line that I'm moving along as I'm calculating my derivative. Well then, what is it we're trying to calculate? We're trying to calculate the slope of this line. And this line is in the same plane as this line. So what I'm looking for is, what is df by ds? Where s is a small change along this line. That's why I used s here, because it makes more sense to talk about arc length, distance along this line. I travel a little bit of distance along this line. How much does f change? That's what I'm looking for. The directional derivative is df. That's how much my function is changing, and that's z, as a result of a change in s, which is an arc length along this line in the xy plane as I move in this direction of u hat. Okay? Because if I drew this plane flat on, okay, here's the plane as I'm looking at it from 90 degrees. So I'm looking at it from this direction here. I'm looking at it like this, okay, this plane. Well, what do I got in that plane? I've got, here's my line, and u hat is pointing like this, okay? And here's this tangent line. It's also in the same plane. It's like that, okay? So if I'm moving in this direction, that's my positive movement direction. We said that that's called plus s, okay? And so I'm actually finding the slope of this line. That's what I'm looking for. That's the directional derivative, df by ds, right? Where this is my f-axis, which is really just the z-axis. Or it can be thought of as the z-axis, okay? So I'm just looking, if I look at that plane in 2 dimensions, it's just the slope of that line. Okay. Okay. Well, how do we actually calculate it? Or let's first write down the notation. How do we don't write df by ds. We make it clear that it's a directional derivative by writing df by ds in the direction of u hat, because I can calculate df by ds in any direction. I indicate which direction by this unit vector u hat at a point p0. Okay? Because I can calculate the directional derivative at any point and in any direction. So I got to specify the direction and the point I'm calculating it at. So that's one of the notations we use. Or maybe a little more commonly is we use a capital D, I don't know, directional derivative, 2 Ds, make it a capital D, directional derivative in the direction of u hat of the function f at point p naught. That's another notation that we use. So make sure you're familiar with both of those. Both of those mean a directional derivative. And you have to calculate the directional derivative, you have to have 2 pieces of information. Well, 3, you have to have the function f, obviously. You have to have the direction u hat, and you have to have the point p naught, if you want to find the directional derivative at a particular point, okay? And if we write down the formal definition, well then d u hat of the function f, it's a limit again, as h, we're going to use an h, where f at x plus ah, y plus bh, minus f of xy, all over h. Okay, where u hat is equal to a comma b. Okay, so we can take the derivative in any direction, meaning we change x a little bit, and we change y a little bit. Okay? And how much do we change them by? Well, h is some very increasingly small number times a, where a is the x component of the direction in which we're finding the derivative, and b is the y component. So we change x by a times h. We change y by b times h. Okay? Minus the function value at the original coordinates xy divided by h as h gets really, really small. Okay? All right, so how do we actually calculate this thing? It's dead easy, thankfully. Calculation of the directional derivative of UF. It's the dot product of the gradient of the function with the unit vector u hat. Okay, that's how we calculate the directional derivative. It's really simple. It's a dot product. So we're finding a derivative. So the gradient of f gives us that's really a derivative, right? That's a vector containing the partial derivatives of f in every direction, x and y, or in each of the two directions, x and y. And you dot that with the direction that you're taking the derivative in. Okay? There's a proof in the notes if you want using the chain rule. You can look at that. Okay, if we want to find, this will give us an expression for the directional derivative. If we want to find out what it is at a particular point, say the point P naught, where P naught are the coordinates x naught, y naught. Well, that's the derivative of f with respect to s in the direction of u hat at the point P naught. So where does that x naught and y naught come in? Well, it's going to come in the gradient. The gradient of f is going to give us a vector, and presumably that vector will have expressions in it of x and y. So you substitute the values x naught or y naught for those x and y in the gradient, and that gives you that dot u hat. Okay? All right, so let's look at an example. We've got a function f of xy is equal to x e to the y plus cos of x times y. We want to find the directional derivative of that at the point 2, 0. In the direction of a vector v is equal to 3i hat minus 4j hat. So we're given everything. We're given the function, the point, and a vector, in the direction of which we need to find the derivative. Very common error I see on exams and quizzes and stuff is people, they just use this vector in the dot product and they think they're done. Remember, this is a unit vector. It needs to have a magnitude of 1. Is this a unit vector? No, it is not. This does not have a magnitude of 1, right? This has a magnitude of 3 squared plus 4 squared square root. It has a magnitude of 5, right? 9 plus 16 is 25 square root of 5, right? So we need to make a unit vector first by dividing it by its magnitude. Now it's a unit vector. So don't forget to do that. Okay, well, the directional derivative in the direction of u hat of f is going to be equal to the gradient of f dot this v hat. So what is the gradient? The gradient is a vector. Is it going to be a 2-dimensional or 3-dimensional vector? Look at your function. Two-dimensional, right? We can take the partial derivative of this with respect to x. That'll give us our x component. And then we take the partial derivative of this with respect to y, and that'll give us the y component. So the gradient vector will be a two-dimensional vector. First component is the partial derivative of our function with respect to x, which is going to be e to the y plus the derivative of cos xy is negative sine y, sine of xy, times the derivative of x of what's inside, which is simply y. And the partial derivative of our function with respect to y is going to be x e to the y. We're taking the derivative with respect to y. And then we've got cos xy, so that's again going to be minus sine xy, times the derivative of what's inside with respect to y, which is just going to be x. Dot 3/5 negative 4/5. So when we do that, that's a dot product. That's a dot product, so we're going to end up with a scalar, right? This first term times this term plus this second term times that second term. So we're going to end up with 3/5 e to the y minus I guess I got to put a bracket in there, right? Minus sine of xy times y minus 4/5 times x e to the y minus, I'm going to write that as x sine of xy. Okay, so that's my derivative in the direction of u hat. Okay, it's a scalar because what is a derivative? It's the slope of a line. It's a number, okay? So my directional derivative gives me a number, a scalar. The dot product gives us a scalar. Okay, and now this is the directional derivative at any point xy. I want it at the point 2, 0. So I just substitute 5. Everywhere there's a y, it's a 0 minus the sine of 2 times 0 minus 4/5. X is 2 times e to the 0 minus 2 times the sine of 2 times 0. Okay, and you calculate that out and you get negative 1. So the slope of this function in the direction of of v at that point is equal to negative 1. So that means at that particular point, the function is decreasing because the slope is negative as we move in the direction of the vector v. Any questions about that one? Okay, so it's just the dot product of the gradient of the vector with a unit vector that goes in the direction that we want to take the directional derivative of. Okay, so let's say let's ask the question, what is d u hat f if u hat equals I hat? If I want to take the directional derivative of some function f, and And the direction I want to take it is in the I hat direction. What is I hat? I hat is that unit vector that points in the positive x-axis direction, right? So what does U hat look like? Looks like that, right? Is that a unit vector? Yep, it's got a magnitude of 1. It's pointing in the positive x-axis. So if I take the gradient of f and I take the dot product of that with 1, 0, what am I going to get? The gradient of f is what? It's the partial derivative of f with respect to x, comma, partial derivative of f with respect to y, dot 1, 0. What do I get? I simply get the partial derivative of my function with respect to x, right? And what about if u hat is equal to j hat? Well, u hat is equal to 0, 1, which means the directional derivative in that direction of my function is simply the partial derivative of my function with respect to y. So the partial derivatives we first learned are just special cases of the directional derivative. That's all I'm getting at. Okay, I'm going to skip that stuff. You can look at the nice pictures in the lecture notes if you want, but that's all we really need to know. Okay, so dot product of the gradient vector with a unit vector in the direction you want to take the derivative of. That's your directional derivative. Okay, some properties that make this very useful for us. It's a dot product. So this df by ds in the direction of u hat, or du hat f, is equal to the gradient vector dot this unit vector. Well, and we know a dot product is just the magnitude of the one vector times the magnitude of the second vector times the cos of the angle between those two vectors. Definition of the dot product. And since u is a unit vector, its magnitude is 1, so it's just this. Okay? That's the directional derivative. Theta is the angle between our gradient vector and the direction we're taking the derivative in. Okay, well, because of this cos theta, one thing we can say is that the directional derivative is going to be a maximum when? What's the maximum value that cos theta can have? What's the minimum value that cos theta can have?
0.
-1 is the minimum. The maximum would be +1, right? Cos theta goes between -1 and 1, right? Does this. Between -1 and +1. So the maximum value that cos theta can have is 1, which means the maximum of your directional derivative is equal to what? Magnitude of the gradient vector. That's the maximum value of the directional derivative. And you get that when cos theta is equal to 1, which is when theta is equal to what? At what angle is the cos of theta equal to 1? 0. Okay, so when the angle between the gradient vector and the direction in which you're taking the derivative of is 0, you get the maximum directional derivative. Does that make sense? Well, what did I tell you the gradient vector gives you? The gradient vector tells you the direction in which a function, what? Increases most rapidly. which means its derivative is a maximum in that direction, right? So this makes perfect sense. This is just telling us exactly what we said before, or it's proving what I told you before, that the gradient vector always points in the direction that the function is increasing most rapidly. So if I calculate the gradient vector for my function, I get some vector in space. If I find the directional derivative in that direction, it's going to give me the maximum change, rate of change of that function. Okay, so we knew that before. So our function f of xy increases most rapidly in the direction of our gradient vector. So if we take the directional derivative in the direction of our gradient vector, we get the maximum value for the derivative. Okay, what's the minimum value that the directional derivative can have? Careful. Negative, right? When cos of theta is equal to -1, that gives me my minimum directional derivative, or maximum negative slope, right? So the min of du df is equal to what? Negative of the magnitude of the gradient vector. And we get that when cos of theta is equal to -1. And at what angle is the cos of theta equal to -1? Pi. Okay, so that means my gradient vector is pointing in one direction, and another pen. And the direction in which I'm taking my directional derivative, my u hat, is pointing in the exact opposite direction. The angle between them is pi, 180 degrees, right? Which makes sense, again, because if my gradient vector is pointing in the direction that the function increases most rapidly, well, then the opposite direction must be the direction in which the function decreases most rapidly, right? If I'm standing on a hillside and I'm looking straight uphill, well, how do I look straight downhill? I turn 180 degrees and I look the opposite direction, right? Gradient vector points straight uphill. If I'm taking the directional derivative in the opposite direction, that's going to give me the direction in which the terrain falls away most rapidly, right? So that's the minimum directional derivative, is in the direction opposite to my gradient vector. So f of xy decreases most rapidly when theta equals pi. U hat points in opposite direction to my gradient vector. Okay? Okay, third case. When is my directional derivative equal to 0? So we looked at the case where we got the maximum directional derivatives. That means the biggest positive slope. We looked at the direction where the directional derivative is a minimum. That means the biggest negative slope. What about in the middle, when the directional derivative is equal to 0? Well, when is that going to happen? At what angle? 45 degrees? 90, right, exactly, 90, okay? When theta equals pi by 2, the cos of theta equals 0, which means your directional derivative is 0. Your function isn't changing at in that direction, okay? Which means if my gradient vector is pointing in this direction, and I find the directional derivative in that direction, I get 0. So this is the case where if I'm standing on a hillside, hill goes up in front of me, right? The gradient is still pointing straight up the hill. Well, if I go 90 degrees to that, I'm walking along the side of the hill, right? I'm not going up, I'm not going down. The derivative is 0, right? The slope of the trail I'm walking on is 0. That's all we're talking about. So we can find, if we're given a function, we can find the direction in which at a particular point, we can find the direction that that function increases most rapidly. That's given by the direction of the gradient function. We can find the direction that the function decreases most rapidly. That's 180 degrees from the gradient function. And we can find one or maybe two directions in which the function doesn't change if we move in that direction, okay? All right, so let's do a quick example of that. And then we're basically done with directional derivatives. So we're given the function f of xy is equal to 5 minus x squared minus 2y squared. We're given a point, p0, -1, -1. And we're asked to first of all find the direction of maximum rate of increase of f. Direction of maximum rate of increase of f at the point p0. So that means at that particular point, what direction do I have to go such that the function increases most rapidly? Okay, B, we're going to do the same thing, direction of minimum rate of increase of f at p0. And C, direction or directions, because there could be more than one, giving 0 rate of change. Of f at p naught. Okay, well, it's not crucial, but it always helps to know try to imagine what the function looks like. What is that thing? What does that thing look like? Well, you see x squared and y squared, so right away you start thinking circle, right? But it's x squared minus 2y squared, so maybe that's not a circle, maybe that's an ellipse, right? And you know, z is equal to 5 minus x squared minus 2y squared, which means the negative on the x squared and the minus 2y squared, you know, z equal to x squared, you know what that is. That's an upward-facing parabola. Z equal to minus x squared is a downward-facing parabola. I've got a negative x squared minus 2y squared, so that they're both downward-facing parabolas. And so it looks like I've got a paraboloid, a three-dimensional surface like this, right? If the z-axis is straight up, it kind of does this. So it's an upside-down bowl, but it's not a circular bowl. It's a bowl that has, it's elliptical, okay? So we can imagine without, you know, any software or anything like that, just, you know, we know what parabolas are in 2 dimensions and stuff like that. So it's going to look something, oh, and I'm probably going to get the ellipse wrong, but it's going to look something like this, right? It's a downward-facing bowl. It's not perfectly circular, though, okay? It's a downward-facing paraboloid. This is the z-axis. Do we know where that point is on the z-axis? Can we figure that out? Well, what are x and y equal to at that point? 0. So put 0 in for x and y right here. What do you get? You get z equal to 5, right? So that's kind of what this thing looks like. Okay? So for simpler surfaces like this, you know, by the final exam, you should be able to visualize a little bit what these things look like. Obviously, if it's, you know, cos x cubed, x minus 1 times y squared, you know, stuff like that, who knows, right? But simpler surfaces like this, you should be able to start figuring out what they look like. Okay, so it looks like this. So we're going to find the direction, or we're going to find the maximum rate of increase and decrease, and where the function doesn't change at the point -1, -1. So if this is x and y, -1 and -1, that's over here somewhere. I don't know. Maybe here in the xy plane. So you take that up, and it's on the function there somewhere. Okay, what direction, if you're sitting on that part of the function, you know, the function is a hill, you're sitting on the hillside here on the back of it, at a point on that hill directly above the point -1, -1 in the xy plane, what direction do you have to go for the function to increase most rapidly? Which way is uphill? Well, that's obviously this way. Which way is downhill? It's this way. 0 is going to be going along the side of the hill, something like that. So we already kind of know the directions, okay? Okay, but we can use the actual directional derivative, right? We're going to need the gradient vector of our derivative, of our function at the point -1, -1. So when you take those partial derivatives, you get -2x, you get -4y, okay? At the point -1, -1, that gradient vector is going to be equal to 2, 4. Oh, what am I saying? That's not where the point is. Somebody should have corrected me. I can't do it now. The point is at -1, -1. That's over here. That's going to be over here somewhere. X is equal to -1 in the xy plane, right? -1, -1. Why are you guys letting me get away with stuff like that? Okay. That point -1, it's in the xy plane. It's going to be in this quadrant back here. Okay, so it's on the, so this point on the surface is on the back side of this hill somewhere. Does this gradient vector make sense? It's got to point straight uphill. It does, right? It's got a little bit of an x component. It's got a lot of a y component. It's pointing uphill. Okay, so we can answer part A. What direction do we have to go for maximum rate of increase of f? Well, in the direction of the gradient vector. We're going to use, we always use a unit vector to do that, so that's going to be equal to our gradient vector divided by its magnitude, which is 4 plus 16 is going to be root 20, right? Which is 1 over root 20 is 2 root 5. So we got 1 over root 5, let's just leave the root 5 out front. 1 over root 5, 2 over root 5. Okay, so that's the direction that we would go in the xy plane, because this is a two-dimensional vector. So if you're at this point, -1, -1, you would move in this direction a little bit, or you would move in this direction to go uphill, okay? That's the maximum rate, the direction of maximum rate of increase. It's the direction of the gradient vector. Okay, what about B? Minimum rate of change. Well, we said that was in the opposite direction of the gradient vector. So what is that? It's just negative of that vector, right? So we would move in a negative direction in both x and y by that amount which means we're going in this direction. We're going downhill, right? If we go in this direction, we go downhill on the surface. If we go a little bit in this direction, we go uphill on the surface. Because remember, this point is on the back side of this hill, right? Okay, what about 0? Well, we can already determine how many directions we need to find for a 0 rate of increase, right? Because we know what this thing looks like. That's why, knowing what it looks like often helps you. How many, if I'm at this point here on the hillside, let's put it up here. I'm on the hillside. This is the point on this surface directly above the point -1 on the XY plane. So I'm here. How many directions can I go and not go uphill or downhill? 2, right? I can either go around the hill this way, or I can go around the hill this way. Remember, I'm on the back side of this thing, okay? So I know I'm looking for 2 directions, right? I'm on the hillside, well, I can either walk this way right across the side of the hill, or I can walk this way right across the side of the hill and not go up or down. So I'm looking for 2 directions, I know that. Okay, well, that means my directional derivative has to be equal to 0, sorry. That's what I'm looking for. In what directions is the directional derivative equal to 0? Find me u hat vectors for which the directional derivative is 0. Well, again, that means the gradient of f dot these u hats have to be equal to 0. Okay, and this is at the point -1, -1, when x is equal to -1 and y is equal to -1. Okay, what is my gradient vector at that point? It's 2, 4. Okay? So 2, 4 dot u hat has to be equal to 0. And I'm looking for the u hats for this to be true. What did we do here? Yeah. Okay, well, let's say that my u hat is that. Okay, I'm looking for a and b such that u hat satisfies that equation. So I've got 2, 4 dot ab is equal to 0, which means 2a plus 4b is equal to 0. So what are a and b so that that's true? Yep.
A would be 2, B would be -1.
Yep. Now we're looking for 2 directions, right? We know there's 2 just by what the surface looks like. So can you come up with another value for a and b? Yep, also works, right? Now, would those values of a and b give me a unit vector? No, right? So really, u hat should be equal to 2, -1 over the magnitude of 2, -1. Okay, so that's one answer, which is going to be what? 2 squared plus 1 squared is 5, square root of 5, 1 over root 5, 2, -1. That's a 2, not a z. And the other direction, I'll call this U1, call this U2, is going to be negative 2, 1, divided by its magnitude. Okay, so those are two directions. If you use these U hats, take the dot product of those with 2, 4, you'll get 0. Okay? And you look at, always good to look at your answer, see if it makes sense. Okay, well, we know we're on a hillside. We're looking for these two directions. Right? We're looking for these two directions. What should be their relationship? Well, one should be the negative of the other, right? They're 180 degrees apart, and that's what we got here. So that gives us some confidence we did something right. Okay, so that's directional derivatives. Any questions? Dot product of the gradient with the unit vector in the direction you're finding the derivative of. And we're done. Have a nice weekend. We'll see you Monday.